In Chapter 5, we're going to be discussing things called polynomials and all the things we can discover about them, and I'll give you an introduction to graphing and analyzing them. In order to have an intelligent conversation about them, however, we need to review some properties of exponents, and that's what we'll do today. So going through the warm-up, simplifying these expressions, -2 to the third is the same as -2 times -2 times -2, which is 4 times -2, which is -8. 5 squared minus 4 to the third, 5 squared is 25, minus 3 to the fourth is 81. 25 minus 81 is -56. Evaluate this when x is 4 and y is -3, so -5 times 4 times -3 squared. Order of operations says I need to do exponents first, or I could rewrite this as -5 times 4 times -3 times -3. And multiplying whatever order I choose, I can do -5 times 4 is -20. -3 times -3 is 9, so this should work out to -180. Also looking at some scientific notation, you'll do a little bit of this today in the homework as well. A gigabyte is about 10 to the third megabytes. A music player is 4 gigabytes of memory. About how many megabytes is this? Well, if 1 gig is 10 to the third megabytes, you have 4 gigs, so you should have 4 times 10 to the third megabytes. 4 times 10 to the third is about 4,000 megabytes. Today we're going to spend most of your time evaluating and using and recalling rules of exponents from Algebra 1. Some things that you had in Algebra 1, if we're multiplying, if we're raising a quantity to an exponent, if there's only multiplication inside, then you can quote-unquote distribute the exponent, and here's why. The reason is that all we're doing is multiplying this group times itself, however many times the exponent's there. So you could say, if we multiplied this group 3 times, you'd have, say, -3 squared times 5, -3 squared times 5, -3 squared times 5. And there's only multiplication here. And multiplication is what's called commutative. You can multiply in whatever order you want. So if I multiply all the -3's together, first I can get -3 squared, -3 squared, -3 squared is the same as -3 to the 6th. And 5 times 5 times 5 is the same as 5 to the 3rd power. Also note that there is not, this negative sign is not underneath of parentheses. We want to, if you're thinking calculator, we're going to want to make sure that this 3 is in its own set of parentheses, and that the negative sign is outside because of the way because of the negative sign there's a parentheses grouping the exponent with it. So -3 squared is what this is trying to say. And you can then go and evaluate the remaining expression in your calculator. If we have exponents that are a power of a power, or also notice, but going back, also notice that 2 plus 2 plus 2 is 6. Or if there's only multiplication, then you can add exponents of the same base. Just like 5 to the first times 5 to the first times 5 to the first is 5 to the 1 plus 1 plus 1, 5 to the third. If it's multiplication, well, we can know the same thing. If you write this out as multiplicative factors, you end up with this. You end up with 4 squared times 4 squared times 4 squared, which is 4 to the 2 plus 2 plus 2, which is 4 to the 6th power. Also notice that 4 squared to the 3rd power, if you have power of a power, or you could even call it, say, a piggyback power, 2, 3 is piggybacked with 2, this is the same as 4 4 to the 2 times 3, or 4 to the 6th power. Power of power, we can multiply exponents. And notice that those things are the same. Next problem highlights if we have the same base, then we can multiply. You just combine by adding the powers. Negative 8 to the first power times negative 8 to the third power is the same as negative 8 to the 1 plus 3, which is negative 8 to the fourth power. And also notice in this case the negative 8 is in parentheses, so we'll multiply negative 8 by negative 8 by negative 8 by negative 8, as opposed to the very first example where the negative was not, where we're squaring 3 and then there's like a negative 1 in front. So I got the negative in the first one by negative 1 times negative 1 times negative 1 is still negative 1. Negative 8 to the fourth power in parentheses is the same as 64. It's the same as positive 64 squared, which is a large number. You can calculate that on your own. Division properties work the same way as multiplying. If there's only division or multiplication, we can still you can still use a distributive property. You can prove that to yourself by multiplying 2 ninths times 2 ninths times 2 ninths is 2 times 2 times 2 on top, which is 2 to the third. And 9 times 9 times 9 on the bottom is the same as 9 to the third power. And again, you can evaluate those on your own. Negative exponents. Negative exponents. Negative exponents, hopefully we remember, is the same as you can flip the position on the fraction bar. So what I mean by that is, well, let's evaluate this. So using my rules from before, I could distribute this because there's only division in here, and I can come up with this. I could say this is the same as 1 to the 4 times negative 2, that's their power of power, is 1 to the negative 8. 3 squared to the negative 2 power is same as 3 to the negative 2 times negative 2, which is negative 4. And now, with the negative exponents, I can rewrite this by flipping the position of anything that has a negative exponent of the fraction bar. So what I'm going to do is instead, since 3 to the negative 4 is on bottom, I can rewrite this as 3 to the positive 4. And 1 to the negative 8, I can rewrite as 1 to the positive 8, but now on the other side of the fraction bar. Negative exponent says flip where I'm at on the fraction bar. And from there you can evaluate. So 3 to the 4th is 81, 1 to the 8th is 1, or this thing is just equal to 81. Quick story problem. Federal Reserve gold bar weighs 400 troy ounces. What's the weight of 250,000 gold bars? Well, if I have one weighs 400 ounces and I have 250,000 of them, I can take 400 and multiply it by 250,000. This is going to be a relatively large number here. This is going to come out to pretty good number here. 400 times 250,000, which is 1 with 1, 2, 3, 4, 5, 6, 7, 8 zeros. Or I could write this as 1 times 10 to the 8th power, because there are 8 zeros here. I could have done this entirely in scientific notation, though, if I would have rewritten each of these in what's called scientific notation. So to find the troy ounces weight here, I'll take the leading number, 4, and I'm going to count how many zeros are after it. And I'll make that my power of 10. And this is 400 in scientific notation. And I'll do the same. So I'll put my first number for the number of gold bars, take my first number, decimal, any non-zero number after it, or up until the last, non-zero number. So in this case, there's only one of them. There's a 5. And then how many decimal spots do I need to move, in order to the right, to get this to be 2.5? Well, if I start at the last 0, I go once, twice, 3, 4, 5 times. So this is 10 to the 5th power. And since I multiply them together over there, I can multiply them together over here. And what's convenient about this is now I'm multiplying smaller numbers. So I can multiply 4 and 2.5 gives me 10. 10 to the 2nd times 10 to the 5th is 10 to the 7th power. Oh, and notice that now I have a digit that's non-zero. I have my leading term is bigger than got more than the ones place in it. So if I say rewrite this, 10 is the same as 1 times 10 times 10 to the 7th. Oh, and 10 to the 1st times 10 to the 7th is 1 times 10 to the 8th. Exactly the same thing we just got, but without needing all the zeros and having to recount and so forth. And on to the back side. On the flip side, we're going to still evaluate, but we're going to evaluate, this time we'll throw in some variables as well as instead of just numbers. So we're going to combine as best we can. And again, the rules have not changed. So if the bases are the same, then we can combine bases, and if we're only multiply between, then we can add exponents, multiply bases is the same as adding exponents. And if we power of a power, then we'll multiply exponents. Okay, so in this case, w times w5 times w negative 8 times w6 is the same as w to the 5 minus 8 plus 6, which is the same as w to the 3rd power. Power of a power, and there's just division inside, so I can, if I were thinking this as being multiplied by itself negative 2 times, I can distribute my exponent into here. So this should be the same as c to the negative 2, and d to the negative 4 times negative 2 is positive 8 power. Also note that we're not done because we have negative exponents, so from the front side, if I have a negative exponent, that means I'm going to rewrite this as flipping where this is in the fraction and changing the exponent to a positive. And oh, if I lose it all, then I have a placeholder of a 1. So in this case, the d is a positive exponent, so we're going to leave the d to the 8th power right where it is. C is a negative exponent, so I'm going to flip this over the fraction bar and make the exponent positive. And since there's nothing left over, we have a placeholder, or a 1, as a placeholder. And that circling went very poorly. Same thing, if I have the negative exponents, I'm here, and if I have the negative exponents, then I can simplify this first. Note a to the negative 3rd is the only thing with negative exponent, so I'm going to move that down below, and this is the same as b squared over a to the positive 3rd times a to the 5th. Oh, and same base, multiplied together, that gives me b squared over a to the 5 plus 3, which is 8th power. Also, could have done, since I'm dividing the same base, a and a, if you recall, another rule from Algebra 1 is if I have divided the same base, I can subtract the exponents, and that would have given me, alternatively, that would have given me, say, a to the negative 3 minus 5, subtract the bottom from the top, times b squared, which would be a to the negative 8 b squared. Oh, negative exponent means bring it down below fraction bar, which is exactly what my original answer was. Again, these exponent rules are the same as from Algebra 1. If you're unfamiliar with them, you may want to go back, read through the section, and it'll go in more detail with each of the algebra rules, the exponent rules, or you can revisit the Algebra 1 textbook if you need to as well. Distribute. I like to solve the more complex ones as simplifying inside before I start distributing exponents. So what I'm going to look to do is see if I can't combine any like terms here and simplify what I have inside. So I have an a a squared and an a to the third on top, and I'm dividing bases, this equals subtract exponents. And you can tell that because if I had a squares on the top and two a's on the top and 3 a's on the bottom, well, since the fresh bar is division, you could cancel out all but one of the a's on the bottom. There's no whole numbers to match up with 2 on the bottom. And I could say b to the negative 1 minus, b to the negative 1 divided by b squared is the same as b to the negative 1 minus 2, which is the same as b to the negative 3 over 2a. And again, negative exponent means I can bring down below. So this is the same as placeholder over 2a b to the third. All this is the third power. The reason I simplify inside is now all I need to do is distribute this exponent. And again, since this means multiply this term, the exponent means multiply this term by itself that many times. So I'm doing 1 over 2ab to the third times 1 over 2ab to the third times 1 over 2ab to the third, which is the same as distributing this exponent to each and every term that's there. So I have 1 to the third, over 2 to the third, a to the third, b to the third, to the third, which happens to be 1 over 8, a to the third, b to the 9th power. I'm going to erase this so that I have room to do the other examples here. So bear with me, it's being erased. Multiplying, I'll combine like terms, term by term, and then see what I end up with and simplify from there. So let's see. Anything alike in here that I can combine, I can multiply. Let's see, 7, there's no whole number over here. You could call it a placeholder 1. 7 times 1 is 7. Y squared times y to the negative 4th is y to the 2 plus negative 4. And z to the third times z to the negative 1 is z to the third plus negative 1, which is 7 y to the negative 2's, z to the positive 2's, and negative exponent. So that means I need to flip where that's at in the fraction bar, and if I don't have one, I'll make one. So that's the same as 7, what's on top? 7 in z squared. What's on bottom? A y to the now positive 2. Let's play the same game with this last example as we had in the first. So let's simplify inside, and then we can apply this to the third power. So simplifying inside, dividing is subtract the exponents. So what's really inside is x to the 4 minus 3, y to the negative 2 minus 6. And all that is to the third power because that's on the outside. X to the 4 minus 3 is the same as x to the 1. 2 minus 6 is y to the negative 8. Which is the same as x over y to the positive 8, all to the third power. And using my power of power, I get x to the third. I get y to the 8 times 3, or y to the 24th power. The last question here deals with a situation, and specifically with some spheres here. So we're going to need some background knowledge of volumes of spheres. In order to have an intelligent conversation about this, we need to know something about the planets, and in particular, something about their volume. A planet is basically a sphere. And if you look up the volume of a sphere in your textbook, you get the following formula. You get volume of a sphere is equal to 4/3 pi times the radius cubed to the third power. And we want to compare the relative volumes of Jupiter and Earth. And we can do that because we know the relative radii of the radius of Jupiter and the radius of Earth. Specifically, we know that the radius of Jupiter is equal to 11 times the radius of the Earth. So if we were to compare these two formulas, I could compare what I get when I plug in, say, the radius of Earth into here, which I get if I were to say, start with the Earth. I get, well, the volume of the Earth is just 4/3 pi times the radius of the Earth cubed. Jupiter, on the other hand, well, we have an expression. We could plug in just radius of Jupiter, Rj, or we could substitute in this nice quantity into the volume formula. So the volume of Jupiter is 4/3 pi times 11 radiuses of Earth squared, because 11 radius of Earth is the same as 1 radius of Jupiter. Whoop. And not squared, but to the third power. Well, how are the first two, how is this formula different from this formula? The only thing is that there's an 11 inside of here. So if we were to, say, simplify this radius of Jupiter, well, what we could do is distribute this third power. And what we discover is that the only thing difference between the volume of Jupiter and the volume of Earth is this factor of 11 to the third power, or the volume of Jupiter is 4/3 pi, the radius of Earth to the third power, times 11 to the third power. But this thing is just the volume of the Earth. So what this is claiming, what we're deriving from this formula, is that the volume of Jupiter is equal to 11 to the third times the volume of Earth. Or Jupiter is 11 to the third times the volume of Earth, which the volume 11 to the third power is a relatively large number. 1,331 times as large as the volume of Earth. Because 11 to the third is 1,331 as volume of Jupiter.